So we want to be able to combine capacitors together, and so we know that there are two ways that we can do that. We can combine them either in series or we can combine them in parallel. So let's start by thinking about combining our two capacitors in parallel. And so to begin with, let's review our Kirchhoff's rules, because again, these are going to become sort of fundamental to how we set up figuring out how we can combine our capacitors. So the loop rule again tells us that if you start at a point within your circuit and walk around some loop, that when you keep track of all the changes in potential, when you complete your loop, adding all those up has to be zero. So some of those are going to be increases, some of those are going to be decreases, but when you add them all up, your sum around the loop is always going to be zero. And again, this is just a statement of conservation of energy. Our other rule, of course, is Kirchhoff's junction rule, and that tells us that when we have current entering a junction, that the current that comes into a junction must equal the current that goes out of a junction. Now this is a little bit complicated in terms of thinking about capacitors, because at the moment we're not talking about capacitors as they charge, so there's not a current flow. So we're going to have to reframe this junction rule here in a minute, but we'll see that it'll still effectively work out the same way. So let's take two capacitors and connect them in parallel. And so we know that when we take any circuit element and connect them in parallel, that what happens is that we have current that comes in over here on the left. It reaches this junction point, it splits. Some of the current is going to go towards element 1, the rest of the current is going to go toward element 2, and then it's going to recombine here at the junction. So that the current traveling through element 1 cannot travel through element 2, right? It's going to split and then recombine. In terms of thinking about capacitors, again, we're not at the moment really interested in how the currents flow to charge capacitors. So the way that we're going to say this is that when we have capacitors in parallel, you have pulled charge out of the battery, you have placed charge on those capacitors, and some of the charge you pulled out of the battery went to element 1 and the rest went to element 2. So it's the same sort of idea. You can't do both. We're not really thinking about the charge moving, we're thinking about the charge stored. So you can sort of rethink of this that when we're connecting capacitors in parallel, that what we're doing is we're taking some charge out of the battery or within our circuit, and we're splitting it so that some of it is stored on capacitor 1, the rest of it is stored on capacitor 2. So when I think about that in terms of a simple circuit like this one, so here I've got a battery, I've got capacitor 1, I've got capacitor 2. Whatever charge came out, some of it got stored on capacitor 1, the rest of it got stored on capacitor 2. And so this, if I apply my loop rule here, I'll start here in the bottom left-hand corner. I'll go around this smallest loop first, and again I have a potential increase as I go across the battery from a negative to a positive plate, but I have a potential decrease as I go across the capacitor from positive to negative. And so that gives me an equation that says that the voltage of the battery minus this voltage drop across capacitor 1, that's got to equal 0. I can pick a second loop. So again, start down here in the bottom left corner of my circuit. And now I'm going to go across the battery. I'll have a potential increase there. I'll go from positive plate to negative plate across capacitor 2, so there's a potential drop. Again, that gets me all the way around my loop, and so I have a second equation that tells me that the voltage of the battery is equal to the voltage drop across capacitor 2. And so obviously what this indicates is that the voltage drop across both capacitors, if they're connected in parallel, has to be the same. So capacitors in parallel have the same potential difference, same V. If I now take that information, so I know that capacitor 1 and capacitor 2 have the same voltage, it happens to be the same as the voltage of the battery, and so now I can think about applying my junction rule. Well, I can start by redrawing my circuit. And so I know that when I combine my two capacitors, I'm going to have an equivalent capacitor that sort of replaces them. So I have my circuit on the left drawn here that shows the two individual capacitors C1 and C2, and then I've redrawn the circuit on the right where now I've combined them into this single equivalent capacitor. And so if I want to think about this modified junction rule that we're applying, well, our junction rule says that when you think about here, this is a junction point, and so it means that charges stored on this plate and charges stored on that plate have to add up. So you can think about, hey, we've pulled some charge out of the battery. Some of that went onto charge 1, the rest of it went onto charge 2. And so again, this gives us an equation that says that the charge coming out of the battery is equal to the sum of the charges on the individual plates. Well, if I apply that junction rule to my circuit on the right here, where I've drawn in the equivalent capacitor, there is no junction. So this one's pretty straightforward. It just tells us that whatever charge you pulled out of the battery has to be put onto this equivalent capacitor. And so, of course, if the charge that we pulled out of the battery equals Q1 plus Q2 on the one hand and Q equivalent on the other, that means that those two things must be equal. I can now use my fundamental relationship for capacitors, so Q equals CV, and because I know that all these have the same potential, that means I've got the equivalent charge is the equivalent capacitance times the voltage. That's equal to Q1 is C1 times the voltage, plus Q2 is C2 times the voltage, and those voltages are all the same value, so they cancel out. So I'm left with my rule for calculating the equivalent capacitance of capacitors in parallel, which tells me that CEQ, the equivalent capacitance of the combined capacitor, is equal to the sum of the individual capacitors. So what this equation tells me is the capacitance of the equivalent capacitor will always be greater than any of the individual capacitances of the capacitors that I've combined to create my equivalent capacitor.